minute.
All right.
I told Robbie I'd be here at 8:45 and missed my bus, so it was like rushing.
Did you get any news from Eric or Thomas?
From Thomas?
Oh,
Friso?
no.
No. Oh, why?
What about Jörg? When?
I think probably they will come today.
Today?
I suppose, yeah. Today. Yeah. So I think there's a reception in the evening. Are you on the campus in Fordham or? Are you in Fordham?
Yeah.
Okay, that's great. I'm in a hotel, but it's not far away actually from Fordham.
I don't know
It's
how
not-
Robbie's
how
gonna
long
be.
is it?
Yeah. He had 2 calls to make. So
Yeah.
I should just do it.
All right. Okay. All right. Ready. Okay. So this morning, thanks for coming again. We welcomed Moulay Barkatou from the University d'Edinburgh. Hope I say it right.
Yeah.
So he will be talking about the algorithm for rational solutions of linear differential and different systems.
Okay. Thank you for giving me this opportunity to talk to you today. And I'd like to thank Alexei in particular. He asked me to talk about this topic.
Very nice.
And so it's not so fresh. The results that are quite old now.
We all come here to learn.
Okay. So what I want to talk about today is rational solutions for systems of linear functional equations that are given in this form. So delta of y m times y plus f. Y is a vector with n components that are the unknown functions. And m is a matrix with entries in some field of functions. And f is a vector with n components. And in the differential case, we have delta is just a derivation. Think of k as rational functions over some field C of characteristic 0. And in difference case, delta is phi minus identity, where phi is, for example, the shift operator. So they act, of course, component-wise. And in the Q difference case, the delta could be phi minus identity, other thing here, but the phi is the operator that maps x to Q times x. And a rational solution of such a system is vector solutions whose components are in K. And we are interested in algorithm for computing these rational solutions. So the overview of my talk, so I split this in, say, 3 parts. I will, the beginning, focus on the differential case, because this is the case most of people are used to. And I'll say some words about the cyclic vector method, which decouple a system or reduce a given system to a single equation. Then I will talk about polynomial solution, how to find polynomial solutions for differential system, rational solutions, and give some complexity estimates in this part 1. Then I will move to part 2 and talk about one of the things that, okay, the differential equations, difference equations, and Q-difference equations share, of course, a lot of things. For example, finding polynomial solutions or local solutions at infinity, they behave in the same way, so they are analogous in that sense. But they have also some differences, and we will see that, for example, computing the denominators of rational solutions is done in a different way in the difference case and the Q-difference case. And I am interested in direct method to compute these solutions, which means without reducing the equation to a single equation, okay, the system to a single equation. And this approach I developed several years ago. Uses so-called reduced forms. So the idea is to start from a system, compute an equivalent system which is simpler in some sense, and then get all the information we need from the new system. So I decided that, okay, instead of what is announced in the abstract, I announced that I will talk about rational solutions and more general solutions. But I think that to keep the coherence of the talk, I decided to give some details on how this reduces form generalized to difference and Q-difference case, and then show you as an application how to compute polynomial solution for Q-difference systems as an application of this reduced form. So let's start by a few basics. So given a system in this form, when studying this system, we use a change of unknown function y equals t times z. Z is a new unknown function, so this is a linear substitution. And when you do this, you get a new system, which is given by this formula. So the matrix M is replaced by this new matrix, and okay, with the convention that in the differential case, the phi is the identity. Okay, and these two systems are called equivalent. So this.
So this transformation works for all three cases.
Yeah, yeah. In this setting, yeah, it works for all these three classes and more general systems. Okay, and okay, the idea behind this is we will use this change of basis or this kind of transformation in order to, given a system, transform this system to a system which is simpler. And simpler, I will say what is simpler.
May I ask questions?
Oh, yeah, of course.
So in the difference case or the Q difference case,
Yeah.
so your phi, no, sorry, I mixed it up. Sorry.
The phi is in the...
Phi is the identity.
Yeah.
That's
In
an
differential.
There's a shift,
Yeah.
for instance. Yeah.
Phi,
Right.
in the difference case, phi is of phi of y of x
Yeah.
is y of x plus 1. Could be x minus 1 or any.
Right.
But
Yes.
phi is a automorphism of k. And
Okay,
okay, and the Q
I mix
difference.
up with delta. I mix things up with delta. Okay,
Yeah,
sorry.
the delta.
The delta is the y minus y.
Yeah, and
Dt y.
delta is in fact what is called a phi derivation.
Right, okay.
So additive map
That's good.
plus
Thanks.
Leibniz rule.
Thank you.
Okay, and this is in general, you know, phi minus identity multiplied by some constant here or some element. Okay, but you can always suppose that phi is given. And okay, so there are differential systems or differential equations can be represented as a scalar differential equation. So this is a single equation of order n, and y is a scalar function, a non-function. And of course, we can, given such an equation, we can write it as a first order system in the standard way. Okay, so this historical this procedure, and the matrix C is the companion matrix of the operator here. Okay, and it's given. So of course, scalar equations are part of systems in general, but the converse is true. Any system, and it works for differential difference case and Q difference case, any system in this form can be reduced to a single equation in the sense that there exists always a transformation y equal to z with t in with coefficients in k that reduces such a system to a single equation, to a system on this form, with C this form. And this result is known as, in the differential case, as the cyclic vector lemma. Okay? I will tell more about this in a few minutes. And this result goes back to Kopp and differential case, and you have various proofs, more or less constructive of this fact, due to, for example, Doreen, Ramis, Katz, myself, and Churchill Kovacic. There is a good paper here about this cyclic vector lemma and how to construct this cyclic vector. And in different case, the result goes back to Birkhoff in 1930, and there are also different proofs. So, with this in mind, let's now move to the differential case. So we'll talk about differential case first, and the polynomial solution and rational solution for differential case. So here again, I just recall that we can have differential equations to form single equations or systems. So this I can skip, and the two forms are equivalent in the sense I precised before. Let me focus on homogeneous equations. The same works for inhomogeneous equations. So scalar equation is given by such a equation and a differential system with this notation. And in here, the system. Okay.
May I ask a question?
Yeah.
That equivalence depends on the cyclic vector lemma, right? Or the converse.
Oh yeah. Yes.
So, that,
Yeah.
so you may want to have some conditions on the field K.
Yeah. Of course, I will state the theorem exactly. But yeah, okay. Yeah.
Very
The field must contain a non-constant. Yeah.
Right.
Otherwise, you have linear algebra. It doesn't work. You know that. And the field here would be C of x, C being a constant field containing Q and say contained in the complex number field. So this is just for the notation, the equivalent system in the differential case. So this is called the Gauss transformation sometime. And I will denote system A by A between brackets. And when I apply a transformation T, then the T of A is by definition this. And this is a equivalence relation. Okay, and the system A and B are called equivalent.
It's called Levy similarity. Levy.
Yeah, I can call this Levy similarity too. Okay. Yeah. Okay, now let's talk about cyclic vectors in the differential case. So the theorem I mentioned is this. Yes, some that there is some non-constant elements in K. K is a general differential field. Then every system is equivalent to a scalar differential equation, in the sense that we can construct T in ln of K such that the resultant system has a matrix in this form. So you have a differential equation.
Now, is this true in positive characteristic or only in characteristic?
It is true also in positive characteristic,
Okay.
Provided that the size of the system, I think, is big enough. N is the size of the system is bigger than, I think, than the characteristic, to avoid some problems. So it works. And now let me show you how to, in practice, how to construct a cyclic vector. So the idea is very elementary, and this is the way Copy 1936 explains things, more or less. So the idea is you have this unknown vector function, and if you take a linear combination of the components, the lambda i's are function in K to be determined. And then you write this linear combination as the inner product lambda times y, and you compute, you differentiate y successively from 1 to n. Then you get the relations, okay, y prime equal lambda 1 y, and etc. The delta to the I, y equal to this vector lambda I, and they are defined by these relations, okay? And the idea is that you get here n plus 1 vectors from lambda 0 to lambda n, vectors in n-dimensional space, then they should be linearly dependent. And you have this is the, and so if you consider this, the matrix, you know, whose rows are given by the original, the given vector lambda 0, and the vector that we construct from it by this recurrence, then if you get this P and you put Z equal to, okay, this vector, and B is the matrix starting from, this is the first row and last row, then these relations can be written in a matrix way as Z equal P times Y, and delta Z equal B times Y, where B is exactly the derivative of P plus P times A. And so, in order that this system be, this system, this one, but you can replace Y by P minus 1 Z. Yeah, you need, in order to get an equivalent system, you need this P be invertible. So the vector lambda is said to be cyclic if this P is not singular here. Okay, if you need that vectors are linearly independent. And then if you replace Y by P inverse times Z, then you get a system with a company matrix as C. Okay. So any system is equivalent to a scalar differential equations. Okay, provided, okay, of course, that cyclic vector exists. But, and you can prove that it is always possible to choose a cyclic vector lambda whose components are polynomial in X of degree at most n minus 1. So this is there are several proofs for this. Okay, and of course the equation you get here is not unique, but all these equations share the same a lot of, okay, they have the same I don't know formal invariance, and of course they are equivalent, so they have the same normal form. Okay, so let me show you an example. So you take this matrix A, 3 by 3 matrix, and you take, for example, the first of this vector 1 0 0, and you compute the sequence.
So, sorry, generically, do you usually find the cyclic vector? So if I just make up some random numbers, then will it typically give a cyclic vector, or? Yeah,
generically, yes, in the sense that the set of cyclic vector is very skilled. So but but there is there are algorithms to construct.
Sure.
The approach here is just take one and try, and and you can. This result is very important. You can always choose this. You are sure that you can find one.
These answers.
Yeah. Okay. And this is just to show you. If you do this here and you compute the matrix P, so this lambda 0, lambda 1, and lambda 2 in this case, and it turns out that this matrix has a determinant non equal to 0. You see the determinant here. So this is a cyclic vector. And if you compute the inverse of P and you apply this, okay, transformation, then you get a scalar equivalent scalar equation, and here you have the. And of course, the example is meant to show you that, okay, it's good to transform a system to an equation, okay? There is no canonical way to do it, so this is the problem. So if you choose any cyclic vector, you can get rather complicated. You know, you compare, okay? And of course, we can show examples with, you know, when one coefficient takes several pages, of course, to write down. Okay.
So there's not any measure of saying something like C0, Z1, Z2 is simpler, in the sense that it makes the equation easier to solve or something?
Yeah, I don't know about this. Yeah, people tried, you know, for several years to find some.
Optimal,
Yeah, some optimal. But this is, I don't know. This is like a primitive element for a field extension. So if you have a way to, yeah, it's exactly the same situation. I don't know if there is a good choice of.
Right.
So it depends of a lot of. So it's not difficult to estimate the algebraic arithmetic complexity. You need n to the 5 operation to compute a cyclic vector and the corresponding scalar equation. And if, for example, you start with a cyclic vector polynomial of degree lambda here, then the degree of the coefficients can be estimated. The bound is this.
Excuse me, what is D0 here?
No, it's the degree. It's the degree. This is, no, it's just notation. This is degree of A. Okay, maximum of the degree of the entries. Okay, and the size of the coefficients. You see here, it depends on the. Sorry. Okay, so if you take the degree of lambda as of order n, then you see that here you have some here n to the cube, times degree of A.
Is there some research on choosing a good cyclic vector?
No. This is for any.
Yeah, but is there some research on how to pick good cyclic vectors?
No, this is the question that we have. And I said that I don't. I don't know.
Optimality, well, the thing is, optimality in what sense?
Yeah.
Right. I'm going to define that first.
A has polynomial entries or rational?
Well, the degree of
A.
Yeah,
But the ultimate goal is to solve equations.
Sure.
So
here is
maybe a high degree is easy.
yeah, polynomial rationality. Yeah. Okay, this is true for A with polynomial entries. If it is in rational entries, then sorry. You can if you have A, say some denominator A tilde, then you can write the system as d delta y A tilde y, and now this A tilde is with polynomial coefficients, and you take this as derivation, and you get a cyclic vector with scalar equation with derivation d times. Okay, so you can give estimates also, and in terms of in terms of the degree of A as a rational function. Okay. So of course, the interest of cyclic vector is that many algorithmic problems are easily solvable for scalar equations than for systems. And this is why people are tempted to, when they have a system, then just transform it to a scalar equation and apply implementation for,
I'm sorry, so then how do you go back to that cyclic vector for the A? Like I understand that you change the derivation and find the cyclic vector.
Yeah, the idea is to transform a system to a single equation.
Yeah.
And it applies with any derivation. So if you start with the derivation d over dx, and you have it's not the optimal way to do it, but just to make a proof, you can factor out the denominator and work with, say, d of x. This is as derivation. So your new delta is this. So you get equation psi d to the I. This is a single equation. And this can be rewritten as psi tilde, okay, d over dx. So the goal is to get a single equation, a single differential equation. Well, whatever the derivation is, it's not a matter. So you can deduce this kind of estimate for any system. So of course the drawback is the complexity, and this is I told about. And in practice, system is large if the dimension is bigger than n equal to 10. Then, yeah?
But it's polynomial time, isn't it?
Yeah, it's polynomial.
Oh.
And okay, my message here is that direct method ought to be preferred then. This is how I gain my life, the direct method. But, for example, okay, it depends on the problem you want to solve. If you have a 2x2 system or 4x4 system, and you can of course transform this to a scalar equation and use. But even if you have a small system, and you are interested, for example, to some problems like find the Liouvillean solutions, or I don't know, asking if some given Hamiltonian system is integrable, then you normalize and get a linear system, and you have to get information about this linear system. In general, the question you ask can be reduced to is an auxiliary system constructed by tensor constructions, symmetric powers, has a rational solution. So in practice, the system that you have for which you want to know if there is a rational solution is a huge system, even if it is sparse. So you cannot always apply this transformation from using cyclic vectors. So now I'm going to talk about how to solve, for example, rational solutions using direct method. So, previous results. So there is an algorithm by Abramov, and there are variants of this algorithm after these days by Abramov and Bronstein and Kwiatkowski, for example. So for scalar equation, okay. So what Abramov and others proposed is, okay, just uncoupling system using cyclic vector, for example, and apply their methods. And the method I'm going to present to you, which is the direct method, goes back to 1996 and was published in 1999. But the result goes back to this. And okay, I will explain now how it works. So the algorithm consists, as usual, for find the rational solution, first find the denominator for this rational solution. What's called here a universal denominator. Okay, and then once you have the denominator, then the problem reduces to find polynomial solutions for a transformed system. And to find the polynomial solutions, you need to bound the degree of the polynomial solutions. This bound of the degree is, in fact, so-called a local exponent at infinity. So it's a root of so-called initial equation. So this initial equation for scalar equation, you can get it immediately from the dominant terms of the equation. So this is why scalar equations are easier. But for a system, this information is hidden in the system. So you have to transform the system. You cannot get immediately this information from the system. You have to transform it using this equivalence relation, change of basis, in order to get a system which is simple in the sense that you can get the information about the local exponents. Okay. Once you have this bound for the degree of the polynomial solution, then you can determine the coefficients. Of course, the naive way is to say, okay, you use just undetermined coefficients and solve. This is not the optimal one. I will talk about another way to get terms one after another. And then once you have this, you can go back to the original system and combine and get the solution. So this is the overview of this algorithm. Also, this start with polynomial solution. So to simplify things, I will consider here, but the method works and it's presented in the paper for a non-homogeneous system. But let's just suppose that the system is homogeneous, and I will work with this derivation, earlier derivation, x over dx instead of the standard derivation because it's more convenient.
Sure.
Okay. Okay. So polynomial solutions are solutions with entries in C of x. Okay, let's call this C of x. It could be, it's not necessarily a complex number, but to simplify things in this presentation, just take this. And we want to construct the space of polynomial solutions. And as explained, I need to find this bound n on the degree of polynomial solutions. So this I think I said about. So this initial equations, no, so this n is a root of a so-called initial equations, and this initial equations is not immediately apparent for a given system. So I need to transform this to what I call the simple form. Okay, and I will show you that every system form can be reduced to every general system can be reduced to an equivalent simple one, and explain you how does it work. So let me recall you what is the initial equation for scalar operator. Maybe it's so it's so for a rational function, u over v are polynomial. The degree is the usual degree, the difference of degrees of numerator and denominator. Okay, and I will write. Okay, this is deg of a. Excuse me. So this each rational function can be expanded as a Lorentz series at infinity, and the leading coefficient will be denoted a bar. Okay. And if now I consider a linear differential operator with respect to theta here, with coefficient ai's in C of x, then the idea is to, as a polynomial is a sum of monomials, then look at the action of L on a monomial. Right? So when you compute L of C x to the lambda, x to the lambda is an eigenfunction for the theta function. Theta of x to the lambda is exactly lambda x to the power lambda. And if you just compute L of c x to the lambda, c is a constant here, then if you denote by h the maximum degrees of the coefficients of L, then it's easy to see that L of x to the lambda is power series in 1 over x, okay? And its dominant term is if this form, x to the lambda plus h is this quantity, some polynomial here, e infinity of lambda times c, and the dots stands for terms of lower degree, okay? And this e of lambda is exactly given by this formula, so you get it immediately from the equation. And this is the so-called initial polynomial. Okay, this is the initial equation, and it is a non-zero polynomial.
Is this different from the method of Frobenius?
Yeah.
This is exactly
This is exactly the The idea is to view a polynomial solution as a local solution at infinity. Okay, in the work by Abramov and Bronstein and so on, they view a polynomial as a series at the origin whose coefficients are zero starting from. So this is, from my point of view, is not the good way. Because if you want to generalize this to this kind of systems, the only fixed singularity for difference and Q-difference equations is infinity, and not the finite singularity. This is the difference between the differential case and so the good way is to look at this as a local solution at infinity. So it's the Frobenius method for if you look for solutions, local Frobenius series solutions at infinity, Okay, then you get that the exponent lambda must be a root of the initial equation. So of course, Frobenius method works for systems with regular singularities. You are sure that this initial equation in that case is of degree n, but in general, this is of degree less or equal to n. It might be that this is just a constant and it has no roots. So this means that there is no local power Lorentz series solutions, or so no polynomial solutions. So now let's move to systems. So the difference between scalar equation and system is that you have an analog of Frobenius method for systems, but it works only for the so-called first kind singularity. Okay, this is when the A, so for the infinity, the A is a Taylor series in 1 over x. So, okay, so A is holomorphic at infinity. Okay, but in general, there is no mean to get this, local exponential without transforming the system, as far as I know. And this is what I propose. So the idea is, a polynomial solution of degree n, can be used as Frobenius series. Frobenius series is series like this. So, at x equal to infinity with the exponent lambda 0 equal negative or n. So let's look at how to find this local Frobenius series at infinity. So I'm seeking a solution, a local solution of my system here, which looks like this. Okay, so the y hat i's are constant vectors. Okay, y hat 0 is non-zero, and lambda 0 is to be determined. These are a complex number. Okay, here to be determined in order that this solves the equation. Okay. So here, if you plug this directly in the system and look, arrange coefficients and equate to 0 on the right equation, then you will get a set of equations, a finite set of equations that from the beginning, the first equations, you cannot get immediately a conditional lambda 0. Unlike the case here where, you get immediately that lambda must be root of this. You don't have this in the case of a system. So the idea is, this is a bit technical, but it's not difficult to understand. I look at each equation. So system has n equations. So first equation, and I just multiply. So we have delta, a theta of y1, ay1, it looks like this. Okay, and so on. So the idea is to look at those are the matrix A is in a rational function, okay, and we expand this A as a Lorentz series at infinity, 1 over x, okay. And what I do here is just take the order, multiply each equation by some, I call this alpha, so alpha 1 and alpha 2, etc. are defined here. I just multiply the equation by a convenient power of x, so that now each of these are Taylor series in 1 over x. They are defined at x equal to infinity. Just this. I get rid of denominators. Okay, singular part. So now my equation can be written now, my system, as a system in this form. Okay, d of x theta minus c of x y. And what I gain here I gained here is that now D of x and C of x are, okay, of course they are matrices. This is entries are in, so, okay, this is to the n times n. Okay, so now D of x and C of x are matrices whose entries are Taylor series on 1 over x. So if you put x equal to infinity, you get a C0 and D0 here. And now if you plug this expansion in this system here, you look at the action of L, this calligraphic L to y hat, you get x to the lambda minus lambda 0 and expansion here, a 1 over x adic expansion, and the 0 cell is given by this. So remember that y hat 0 is supposed to be non-zero, okay? And one necessary condition in order that y hat be a solution is that this equation must be satisfied. So here you have a pencil of matrices, okay? And as y hat 0 is non-zero, the determinant of this pencil must be 0. Okay. So we have a candidate for our initial equation. Just take the determinant of, so we compute a D0 and C0, and take this determinant. So this is a polynomial in lambda of degree at most n, and so lambda 0 must be a root of this. Okay. The only problem, so okay, this is what is written in this slide. So I put this by definition E infinity of lambda is this determinant. So if y is a non-zero polynomial solution, and more generally if it is a local solution at infinity, a Frobenius solution at infinity, then the exponent, okay, or the degree of polynomial solution must be, or its negative must be a root of this polynomial. So I would like to call this initial equation, but unfortunately it may happen that this determinant here is identically 0. There is no guarantee that it's not. Okay. And this what motivates the following definition. I will call my system a simple system if the corresponding equation here, this determinant is non-zero. If not, it's non-zero. Okay. So if I have a simple system, then the method for scalar equation works. Okay, you just plug. You have a bound for the degree of the polynomial. But if it's not simple, then you have to do something. So the big difference with scalar equation is this. In the case of scalar equation, you get this initial equation with a non-zero polynomial, so it gives you useful information. But here, if it is identically 0, then okay, any complex number is okay. You have no information on them. So, okay, example of simple system. So I mentioned before the so-called first-kind systems. First-kind systems at infinity are systems of this form where A is a Taylor series in 1 over x. So this is the definition. And for these systems, Frobenius methods apply, and you can compute this Frobenius series with analysis of Frobenius method. Okay, and in this case, in fact, the local exponents at a first-kind singularity are just the eigenvalues of the residue matrix here. So you take A0, and you have immediately your initial equation. And in this case, if I apply my method, what I get here is that D0, as already this is in the good ring, I do not need to multiply on the left by any powers of x. So the D0 is the identity, even D is the identity, and the C of x is A, and C0 is A0. So this is a polynomial degree exactly n. And so each system of first kind is a simple system, and the initial equation is the one we are expecting. Okay. This is true too for systems that are associated to a single equation. If you start with a single operator, scalar equation, and you write the companion matrix, and you apply this method, you get D0, 1, 1, 1, and epsilon either 0 or 1, it depends, and C0 is given by, okay, this is the, oh, sorry, change the, okay, this is, it has the same meaning, right? Right, the leading coefficients at infinity for HA, and the order is minus the degree, right? Okay, this is the order, the 1 over x valuation at infinity. This is a good formulation. So if you do this here, then you get the initial equation of the scalar equation. So this construction leads you to the initial equation for scalar equation when you apply this to scalar equation. Okay? And this is interesting because now, if you remember, any equation, any system can be reduced to a single equation by cyclic vectors. So theoretically, any system is equivalent to a simple system. So I know that any system is equivalent. But the problem here is I do not want to, of course, compute it using a cyclic vector. So otherwise, it's no more simple than that. Anyway, okay. This is an example of a non-simple system. So if you take this 2 by 2 system, okay, and so now I explain again what I did. So look at the first equation. So I have a pole at infinity here of order 3. So I have to multiply the first equation by x to minus 3 in order to kill this. Okay. Here there is no pole, so I just let it as it is, multiply by 1. So my matrix D here is this diagonal matrix, and the resultant C is this. Now my D0 and C0 are these two matrices. The determinant here is identically 0 because there is a 0 columns in this matrix. So you see that, yeah, this determinant can be identically 0. So this is a non-simple system. Now, if I consider this change of basis, this Moulay transformation with this matrix T, for example, and I compute the new equivalent system, now I compute the D0 and C0 corresponding to this immediately. I get that this new system is simple, and the determinant here is non-zero and is equal to the constant minus 2. So this system can be transformed to a simple system, and in this case, the initial equations associated with the simple system is just the polynomial. The initial polynomial is the polynomial minus 2, and this means that there is no local solution, so there is no polynomial solution. Okay. Now I will explain. Okay, this is what is explained here. Okay. The determinant, you compute, do the computation, and you get. And this is not, for example, a regular, of course, this is a second kind singularity. Anyway, so this I said that there is no polynomial solution, excuse me. Now let's back to the general case. I showed you some examples. Now it can be proven that given any system, one can construct a non-singular matrix T, which is polynomial in X, and this is important for the polynomial solutions, such that the gauge transformation turns the first system into a new system which is simple. Okay? So there is okay, I'm not using, of course, the cyclic vector because I said that it's to be a cyclic vector. And this transformation can be constructed using the so-called super-reduction algorithm due to Hilary and Basel and myself will prove it. So there are a lot of works between these 2 days, but anyway, this one is a good reference that gives an alternative way to compute this super-reduction. It's a super-reduced form. And more recently, with my former PhD student, Karol Bashawi, developed an algorithm to compute simple systems without using this super-reduction. I will, in the third part, I will talk about this super-reduction for general systems, differential, Q-difference, and different systems. But, okay, it gives simple system. It gives you this information about local exponent at the singularity. Also, but in fact, it gives more stronger. That is more than what we need.
Do you have
So,
good
yeah.
degree bounds on T?
Here,
Yeah.
yeah. So there is a way, and this I will talk about in the ACA session, about this method to compute this simple system. And remark this fact that T here can be polynomial. Okay, this is important because polynomial. So if you are interested just in polynomial, so they are preserved. Okay. So you look for polynomial solution for the new system, and then you multiply by T, and you get the. Okay. Yeah. Yeah, the degree of T. Yeah, we have a bound. This T. The degree of T is, okay, if you have a system here, for example, this one, with a pole of order 3 at infinity here, okay? So this number 3 is called the Poincaré rank of the system, okay? So the worst case, the degree bound for this polynomial would be this rank multiplied by the size of the system. So it's R times N or less. Okay. So I will tell about this maybe later on. I'm too slow. Okay.
About 40 minutes.
I cannot guarantee that I will talk about all what I announced. No, because I spent more time than, I was planning in the first part. Anyway, so this notion of simple system extends to finite singularity. Remember that to find this rational solution, we need to know the poles and their order of any solution. And this is what I call the universal denominator. And in the differential case, these orders are given by looking at each singularity. So singularity of solutions are singularities of the coefficients, and getting and the local exponents. So you need to transform at each singularity to a simple system and get this information. So this notion is useful for computing the denominator of rational solutions. And to find the so-called regular solutions of formal solutions, Frobenius solutions, we need this too. Okay. So it's computing, not commuting the coefficients of polynomial solutions. Yeah, maybe I will skip this. Okay. The most important thing is to get the bound on the degree of polynomial solutions. Of course, once you have this, you can use undetermined coefficients, but it's not good. The algorithm I proposed 15 years ago works in the following way. Okay, it applies for, I suppose that I transformed, I start with my system and transform this system into a simple system. Now, I start with a simple system here, and B is the right-hand side, okay? Then the idea is to find the Y monomial by monomial. Okay, one of them. And this is in particular interesting if you have sparse solutions. Okay. But it turns out that it works even if the solution does. Okay. It works very well. It's very efficient. So the idea is just, if you plug this in the system, then now Z, the rest of so this is dominant term in Y, and the rest is a solution of a system of same type with now as new right-hand side B, because of the linearity, of course, of the equation. And the idea is to find mu and C in order that what it remains here is of lower order at infinity of degree, lower degree, or higher order, and lower degree at infinity. And okay, I won't show you how to choose C and mu, because it's okay. It's written in the paper, and it's not okay. I have to make some choice today. So let's just say that after a number of steps, you get an equation like this, okay? And you have to solve, so you have a polynomial solution if and only if this right-hand member is 0, and so you have a linear system, algebraic equation to solve, and okay, and this is the idea. Okay, let's move to rational solutions for systems. So again, consider systems with same notations here, and we want the rational solutions, and I explained that we need this universal denominator. Once we have this, then transform to a new system for which we look for polynomial solutions. So, as I said before, what is nice with linear differential equations is that the singularities of solutions are singularities of coefficients. So we know a priori what are the poles of rational solution. Okay, which is not true, as you know, for nonlinear equations, for example. Okay, so we look at, let SA be the set of finite poles. So, and for each pole, I need to know the exponent, the order of this pole. So what we do is just compute, transform at this point the system to a simple system as explained, and then get the initial equation at x0, and then the order of pole is a 0 of this equation, or its negative is a 0. And then you get, for example, for homogeneous system, the universal denominator is given by this product. So it's almost trivial. The only difficulty here is that once you have these initial equations, then everything is easy. Okay. So I have to hurry up. So for the what is the complexity estimate for this algorithm? So this becomes the algorithm to compute universal denominator and compute polynomial solutions. And now, okay, let's state it for homogeneous equation. So the entries are rational functions. So I denote by the norm of A the denominators of matrix A, and its factors, the reducible factors here, Qi, okay, to R sub I. And this R sub I is, called the Poincaré rank, or the order of the singularity of each individual singularities of these roots of this polynomial. Okay. So this you have immediately, this I. So let's D be this quantity, and R infinity is the analogous but at infinity. This is the rank of the singularity at infinity. So this is why I use the same notations. Then the universal denominator can be computed in this number of operations. So n to the 5, n is the size of the matrix, the maximum of Poincaré rank, okay, and times d. Okay, so this is the complexity for computing the universal denominator. And as for polynomial solution, it can be done in this number of operations, n to the 5 again, n infinity squared. So this is the rank of the singularity at infinity, n to the cube, and the n, capital N, is the bound on the degree. So of course the input, the output, and the number of operation depends also on. Okay. And then total, this is the complexity for rational solution using this algorithm. Okay. So you can compare this to the complexity to get a single equation using cyclic vector. So if you want to solve this problem using cyclic vector, you have to transform first the system to a single equation, and this needs n to the 5 operation first. So this is the minimum you need if you use cyclic vector. Then you have to apply any algorithm for solving a scalar equation and add this complexity to the. So in practice, it turns out that this algorithm is very efficient than using, of course, cyclic vector. This is trivial, but it turns out that even I tried to take a single equation, transform this to a first order system, and apply my algorithm to this, and it was faster than